All right, physics guys, this is chapter 13, part 2 video. So continuing on, looking at the center of mass, if you have a weird blob, just a weird shape, weird object, you can find the center of mass this way. So it becomes calculus. It becomes where delta M is approaching 0. So now it's not just a summation, it is an integral, which is an infinite sum of infinitely many infinitely small things. So yeah, so notice it says dm here must be replaced by, this has got to be replaced by something to do with an x, since x is the variable here we've got. It needs to be the variable of integration needs to be x. And here it needs to be replaced with something with y. We'll talk about how that's going to happen. So this is a good example to tell us how it's going to happen. Let me erase what I wrote here a little earlier. Find the center of mass of a thin uniform rod of length L and mass m. Use this result to find the tangential acceleration of one tip of a 1.6 meter long rod that rotates about its center of mass with an angular acceleration of 6 radians per second squared. So we're first trying to find the center of mass of a thin uniform rod of length L and mass m. Okay, so first we want to say that the center of mass is going to be 1 over m times the integral of x dm. Now we got to replace dm. We could say here that as you change x by just a little bit, then the mass is going to change by a little bit. So if you have 0 change in x, you're going to have 0 mass. Like if you're just a line, then you're just going to be no mass. But if you change by just an infinitely small amount, then the mass is going to change by an infinitely small amount. So, and how do we do that? So I could say dx is to dm. And since this is a uniform rod, so the full length of the rod, dx is just the tiniest length of the rod imaginable. The full length of the rod is L, so dx is to dm just as L, the full length of the rod, is to the full mass of the rod. And that's the case. Why? Because it is a uniform rod. So now we can get dm in terms of dx. Let's solve for dm. So if we solve for dm, that means I could multiply both sides by dm. So I'm just going to multiply both sides by dm by putting dm over here. And so now I divide both sides by L over m, which is the same thing as multiplying both sides by m over L. So dm equals m over L dx. Sorry for the scribbling. So that is now going to go here. And I will have not a dm, but a dx, which is what I need. So let me write it right here. The integral now, it's 1 over m. Well, that didn't work. 1 over m is still outside this integral of m, shoot, I should have wrote x m over L dx. And m over L is a constant. So now that comes out. So now it's, when that comes out here, I've got m on top and m on bottom. So now it's just 1 over L. Integral of x dx. Okay, there's my expression that I need to help me find this center. Let's get us some more room. So remember this: 1 over L integral of x dx. Okay, let's clear this thing if we can. One over L integral of x dx. Now, what about the limits of integration? Let's look back and think about that. This integral is going to go from, as x goes from what to what? Well, this is x goes from 0 all the way to the full length of this rod, so all the way to L. So 0 to L are my limits of integration. 0 to L. All right, so let's integrate this thing. Remember how to do an integral? It's just x to the first. We increase that by 1, and so it becomes x squared over 2. So I think it's going to be x squared over 2. Let me just put this as 1 over 2L. I'm going to put the 2 there. From 0 to L. So now I think it's going to be 1 over 2L, L squared minus the 0 squared. So that's gone, right? So now it's just 1 over 2L times L squared. So that's going to cancel with that. So it's just going to be L over 2. And you know what? We kind of knew that at the beginning, but it's cool that we just dadgum figured it out and proved it. Doesn't it make sense that if we have this uniform rod, where would the center of mass be? If this rod goes from 0 to L, that the stinking center of mass is going to be right in the dadgum middle. Boom. And where's that? L over 2. I love it. All right, that's the center of mass. Erase, 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 erase. I love this pen. I bet you can tell that. I'm kind of digging my surface right now. I wasn't earlier, but I kind of am now. This is its element. All right. Now what does it want me to do? It wants me to find the tangential acceleration of one tip. It's 1.6 meter long rod. Rotates about its center of mass. Angular acceleration 6. And we want to find the tangential acceleration. So L equals 1.6 meters. Alpha equals, didn't it say 6? 6 radians per second squared. 6 radians per second squared. And I want to find the tangential acceleration. Well, that's just going to equal alpha r. Well, what is r? Well, if this thing is it wants to find the angular acceleration. No, it wants me to find the tangential acceleration of like this tip, this right here. Well, how far away is that? What is r? That's why it asked us to find this earlier. This is L over 2. So, and I know L. So, A sub T equals 6 times 1.6 over 2. That's going to be a 3. So 3 times 1.6. What is that? 3 times 48. 4.8. I do believe. I'm not good at simple math. I really am not. So I hope that's the right answer. 4.8 meters per second squared. Let's go over here and see if we got it right. Look what I got. they got 1/2 L, which is the same thing as L over 2. And they got 4.8 meters per second squared. Booyah. Okay. This question, I think you're going to get it wrong. Not because I think anything bad about you, but just because it's a tricky, stinking question. A baseball bat is cut in half at its center of mass. Which end is heavier? I bet you're going to say. Say that, because that really seems like the intuitive answer. But it's got to be this end. Why? Because since this is the center of mass, then if this end you can tell is farther away from the center of mass, then in order to make up for that, this has a greater radius, then this has got to have a greater mass, because it's the mass times the radius that gives us the moment of inertia. So again, since this has a smaller radius than this has got to have a bigger mass than this. Let's see if that's right. Yes, it is. The hitting end, the right end. All right. A rotating object has kinetic energy because all particles in the object are in motion. The kinetic energy due to the rotation is called rotational kinetic energy. Adding up the individual kinetic energies and using the fact that V equals omega r, so tangential velocity equals angular velocity times radius. So we can change this. We replace all those V's with R's and W's, and they get squared, so they become R squared, omega squared. I said W, I should have said omega. So it's all that stuff of all those particles. And notice they can factor out the 1/2 and the omega, because those are going to be constant. Because those are constant. Omega is constant as that thing is rotating. And so that's just the sum of all the masses and the radii. So define the object's moment of inertia as all those little particles, the masses times the radii squared. And so if that's how you define that, a moment of inertia there, and that was what was in that kinetic energy equation we just looked at right here, then it just becomes 1/2 times the moment of inertia, which is I omega squared. 1/2 I omega squared instead of 1/2 and V squared is 1/2 I omega squared. Units of the moment of inertia are kilograms times meters squared. The moment of inertia depends on the axis of rotation. Mass farther from the rotation axis contributes more to the moment of inertia than mass that is near the axis. This is not a new form of energy, but it is merely the familiar kinetic energy of motion, just written in a new way. As we did for center of mass, divide a solid object into many small cells of mass delta m. Let delta m approach 0, and now you got yourself an integral. So instead of just delta m's, now we got dm's, and so we got an integral. So the moment of inertia is equal to the integral of r squared dm. And I bet dm is going to have to somehow make it be in terms of r to do it. The good thing about this is, good news, you rarely have to do this, because most of the time common shapes are going to be used, and there are the moments of inertia for common shapes are usually given to you. And here is the slide that gives you lots of moments of inertia for common shapes. And I think this is on the physics test, the AP test formula sheet. Let's take a look at it. Formula sheet. Where are you? Moments of inertia. Where are you, moments of inertia? I didn't see them, but maybe I missed it. I don't know. I don't see it. But I bet on the questions it probably gives it to you. Like in the question, maybe it gives you the moment of inertia for a particular common shape if it uses a common shape. If it doesn't use a common shape, then it's going to have to give you the information you need to do that integral. It's going to have to give you some sort of a function to be able to do it, to do the integral. All right. Consequences of moment of inertia. Mass concentrated at the center. That means it's easier to speed up, whereas mass concentrated around the rim means it's harder to speed up. So if these two things are the same mass, yet if this one has more of that mass concentrated at the center and this one has more of that mass concentrated toward the rim, this one's going to be harder to turn than this one is. Let me give you a really cool illustration of that. A really cool illustration of that is figure skaters. If you notice when figure skaters start into this spin, and then they make themselves skinnier and skinnier, and they lift their arms up so that they're straight up and down, so that they can be the skinniest possible. They are rotating extremely fast because they're taking all that angular momentum and they're decreasing the radius. Same mass, decreasing the radius, which makes the momentum, right? Angular momentum is equal to I omega. So they are, and if this is staying constant, if they decrease I, then that makes omega have to increase to maintain that L. So that's why figure skaters, when they get real skinny, they start spinning really fast, and then when they want to come out of that spin, they are going to slow themselves down that way. All right, watch this. I had to show you. You need to see this.
For decades, the Winter Olympic Games have
angular
drawn
momentum
people
stuff
from
in
across
action.
the world to marvel at breathtaking athletics on the snow and ice. One of the most popular events is figure skating. Athletes meld acrobatics, dance, and physics into mesmerizing performances. It is the sheer precision that separates the skilled athlete from the novice. Through years of tireless training, skaters must learn to understand and use angular momentum to become the best in their sport. Angular momentum is the product of a skater's moment of inertia and angular velocity and is represented by the letter L. When the
Watch
skater
this,
is
Jack.
rotating
This is
with no
going
net external
to
torque
convince you.
acting on her, angular momentum is conserved. With her arms and leg outward, she increases her moment of inertia, which reduces her angular velocity. As she pulls her arms and leg inward, she is able to spin faster since her angular velocity increases while her moment of inertia decreases. And this is how skaters become champions.
And the physics students become awesome. All right, new quick check problem. Which dumbbell has the larger moment of inertia about the midpoint of the rod? The connecting rod is massless. All right, this one has twice the radius. This one has twice the mass. I believe moment of inertia we said was m r squared, so that means I think the answer is B. And it is. All right, the parallel axis theorem. You do sometimes need to know the moment of inertia about an axis in an unusual position, like cams and stuff. You can find it if you know the moment of inertia about a parallel axis through the center of mass. So here's an axis through the center of mass. Here is an axis through a weird spot. So if this thing is rotating around this weird axis, how can we get the moment of inertia? Well, this tells us the moment of inertia about that axis is the moment of inertia about the center of mass plus the entire mass of this thing times this distance between these 2 points squared. That's a pretty neat formula. I thought it might be a good idea to look back at the formula sheet and see what is on here regarding these topics. So here's where kind of angular stuff starts. Centripetal acceleration equals v squared over r, or omega squared r. Something we just talked about. Tau, which is torque, is equal to r cross f, which is the distance times the force in a perpendicular way. All right, alpha, and this is torque equals, the net torque equals I alpha, or F equals ma, tau equals I alpha, but it's just written in a different way because it puts, it solves for alpha, which is, I think, the same way it does force as well. Okay, it gives me the moment of inertia. It gives me that integral formula there. It also gives me the less calculus-y formula here. It's just the sum of all the mr squareds. It gives me a formula for finding the center of mass along a particular axis, whether that's x or y. It just gives me x here. So that's that formula. V equals omega r. We already knew that. Angular momentum, L, equals the linear momentum times the radius, and again in a perpendicular way, where the radius is perpendicular to the tangential or linear momentum, which is also equal to, if linear momentum is mv, then angular momentum is I omega. Angular kinetic energy is 1/2 I omega squared, and then here's just a couple of angular kinematics equations. So it gives us a good bit of stuff on the formula sheet. New example: the speed of a rotating rod. A 1 meter long 200 gram rod is hinged at one end and connected to a wall. It is held out horizontally and then released. What is the speed of the tip of the rod as it hits the wall? Okay. So for this problem, we have a 1 meter long 200 gram rod. So I went ahead and looked back here at this thing to say, okay, a thin rod, and it's not rotating about its center, but about its end. So the moment of inertia for that situation is 1/3 ml squared. So I went ahead and wrote that down right there. All right, so what you have at the beginning is you have this rod sticking straight out from the wall. Then this is the hinge. So, it would want to rotate about its center of mass, but not when it's attached to something. When it's attached to something, it will have to rotate about that hinge. It's going to rotate about that hinge, and it's going to end up like this. So this seems to me to be a conservation of energy, mechanical energy problem, where we have potential energy at the beginning converting to kinetic energy until it smacks the wall. So I'm thinking something along the lines of UI plus KI equals UF plus KF. All right. So this potential energy is based on the position of this rod. And to make things simple, what you can do is you can just treat that rod as if it's just one thing that's concentrated right here at the center of mass. So you can just concentrate it as if it's one object, even one particle located right there at the center of mass. So this is the center mass at the end. I'm going to call the height, the initial height. You could call it what? You could call it whatever you want, I guess. I'm going to call it 0. And I'm going to call this final height then is going to be negative 0.5. Since the whole thing is 1 meter long, it's going to be 0.5 meters lower than where it started. So I could have swapped it up. I could have called this 0 and this positive 0.5. In fact, maybe that makes more sense. But it's arbitrary and it'll work either way. That's the beauty of it. You pick your own origin, and then base everything off that. So let me take this. U sub I is going to be M G H at first. My H at first is 0 plus K sub I is 1/2 I omega squared, which omega at first is 0. So actually those two things both are 0 initially, the way I have it set up. And the final potential is actually going to be negative, which is strange, but it will still work mathematically. So it's M G negative 0.5 plus 1/2 I omega F squared, which is what I'm looking for. I need to find that final omega. If I can find the final omega, I can find the final speed by multiplying by R. Okay, so I think I know everything here. I think I know everything I need to know. This is 0 equals 0.2 times 9.8 times negative 0.5 plus 1/2, and now 1/3 ml squared has to go in for I. So 1/2 times 1/3, and M is 0.2, and L is L for that rod is the length of the rod, so it's 1 squared. So that whole expression there is the I, and then omega F squared. And again, omega is what I'm looking for. So all I got to do is do my arithmetic, multiply that together, move it over, multiply all that mess together, divide it, take the square root, and that should give me omega. Let me pause it and do that in my calculator. I got omega equal to 5.4. And yes, you did see the old computer calculator come up with that, because I can't find my calculator at the moment. So 5.4 is omega. Now I'm going to use that to find the, now let me just clarify something. This is the angular velocity of the center of mass as it hits the wall. But we want to know the speed, not of the center of mass, but of the tip of this rod as it hits the wall. But what's nice about that? What's nice about that is omega is the same. That's angular velocity. It's the same everywhere. That's the rate of change of the angle, and the angle is changing the same for that whole thing. So so it's the same for the tip. So V is going to equal omega R, which is going to be 5.4 times 1, which I think it should be 5.4 meters per second. Let's see if we're right about that. We are 5.4 meters per second. Awesome. Quick check. The four forces shown have the same strength. Which force would be the most effective in opening the door? Here's the hinge. Which force is going to be the most effective opening the door? You probably have a good intuition about this. It's going to be F1. Yeah, this is going to, when you get farther away from the hinge, it makes you better at opening the door. And because this force is angled directly perpendicular to the radius, the lever arm, it's going to help us open the door. This one's not going to be too good because it doesn't have a good radius. This one's not going to be as good because it's not delivering the full force trying to open the door. This one ain't going to do nothing. This one will not do anything to open the door. It's just going to push against the hinge. So good, F1. Torque measures the effectiveness of the force at causing an object to rotate about a pivot. Torque is the rotational equivalent of force. On a bicycle, your foot exerts a torque that rotates the crank. I think we'll save this for a new video. We're going to stop this one, and we'll call this one part 2.